So the next thing is, not all of the stuff that we need, like cadmium or zinc or copper, is available in nature in a bulk form. Some of these materials appear as co-products, or what you'd call a hitchhiker, along with more abundant materials. So it's much like thumbing a ride. You're riding in somebody else's car, so some elements don't occur in nature in a bulk form. They occur with a more abundant material. Let me give you some examples, and this is in your handout. So here we go. So in this handout, what you see are pairs of element. You see cadmium and zinc, right? One is within parentheses. In each pair, the element within parentheses is the parent material, and the one outside, in this case cadmium, is the hitchhiker. So what that means is, cadmium normally is found not on its own, but it's found in ores that bear zinc. And so, getting access or getting availability to cadmium depends on the availability of the zinc-bearing material. And so we call cadmium a hitchhiker resource. It literally gets a ride along with zinc. Now, some elements, their availability or acquisition as hitchhiker is the only means. For others, they do appear to some extent in a bulk form, but predominantly again in the hitchhiker form. The challenge to the availability of these hitchhiker resources is not their own absolute abundance, but rather the abundance of the parent and the rate of use of the parent. So in the case of cadmium and zinc, you may have a reasonable amount of cadmium, but because it occurs with zinc, the faster zinc is used, cadmium also will be proportionately used. And so that's something we need to bear in mind, is, are we dealing with a hitchhiker resource or something that's available on the bulk? So another thing to consider. Next, we'll start discussing depletion times of various resources. We'll first talk about energy sources, right? So for modern technology, you basically have two major requirements. One is, you need to acquire potentially beneficial elements like iron or copper and so forth. The next thing is, you need to convert this into forms that are that can be used by people. For example, iron. You can smelt iron, but people don't just buy iron. Iron has to be converted into steel. Steel has to be rolled into plates and sheets, which then have to be transformed into automobile body panels and other things like your washers and dryers and so forth. So we need to be able to acquire materials, useful materials, and then transform them into useful forms. So as we think about this, we need to see how all of this happens, right? Especially the materials that we may be interested in for purpose of our discussion, that's confined to fuels, fossil fuels especially, because that's our largest source of energy. So the use of fossil fuel dominates our energy needs today, and will do so in the near future as well. So how do we acquire these? Well, we mine them. We acquire this by mining or digging into earth. And a rule of thumb is that for every ton of useful stuff, or stuff on which you want to get your hands upon, you have to remove another 1,000 tons of the stuff that lies above it, called overburden. So for every ton of what you want, you got to displace 1,000 tons. So imagine if you needed 1,000 tons of stuff, then it's 1,000 times 1,000 that you have to. So it's a lot of stuff. So, and this is not easily done. Earth, excavating earth is a very energy intensive process. It takes a lot of energy, and it also does a lot of we are altering the face of the earth, right? You are destroying ecosystems, you're rearranging Earth's face locally. So you're doing a lot of damage whose long-term and sometimes even short-term effects you're not aware of. It's not just acquiring the material you need, this stuff usually inconveniently is located in remote places. Like if you take the US, there's nothing that's available in Boston or San Jose or Seattle or in Austin. They are usually located in Arizona, New Mexico, Utah, Montana, and Colorado. So the stuff that's excavated has to be transported to smelters, who then do ore dressing and then refine iron and make pig iron out of it. Smelting is a very energy intensive process. And then you have transportation of pig iron to secondary manufacturers who then roll out sheets of steel and then transport it again to your automotive manufacturers in Detroit or elsewhere. So the transportation again is energy intensive. So the whole thing is a pretty energy intensive process. So oil is the number one source of fossil fuel. It's followed closely by coal and natural gas. Nuclear energy and hydroelectric account not for a whole lot, a few percentage. And another important thing to know is the percentage of what's called the final energy as compared to the primary energy. So when you extract coal, that coal has some inherent or embodied energy. Now what we use eventually at home and workplace is called the final in the form of electricity. And there's a difference between the two. Typically in 1990 this was about 3/4 of what we use at home. From a 100%, 75% is what is available. What happens to the rest? Well, the process of combustion, the process of moving a turbine, transmission, etc. There are various losses. And a third is used industrially. Let me show you what I mean by this. So this table that you see basically shows you, let's take coal. You see various sources of energy. And these are numbers for 1990. So these are in units of energy in joules per year. So you can see oil is the dominant. You got coal and gas. You got nuclear, hydro. They do make a difference, but not quite in the order of fossil fuels. So again, when you hear this debate about energy and people talking about shutting down this or that plant, you need to have a sense of what comes from where. We can shut down a coal plant. If we don't have an alternative, we may have to contend with not having power for many hours in a day. So out of 91 units of energy, finally what is available is 36. Right? I mean, that's a lot is lost in converting the inherent energy in coal, having it go through a process of combustion, producing superheated steam, turning a steam turbine, and then providing electricity. So lots of losses here. It's not a very efficient process. And industry used about 25 units out of the 36. So industry is a major consumer. Let's talk a little bit more about fossil fuels. So the name suggests, you heard of fossils before in classes. Typically what we have in mind are things like dinosaurs and so forth. The bones are preserved deep in earth. Fossil fuels are sort of the same. They are close cousins of dinosaurs, if you will. It's basically organic stuff, maybe trees and other material that have been buried in earth, deep in earth, and the pressure and temperature causes decay and transformation, producing coal, natural gas, oil, etc. Now, technically, this process is renewable, right? Even as we speak, as we are removing coal from the earth or oil, other materials buried, again, years ago are being transformed into coal and oil. So it is technically renewable, but the process takes billions of years. So if we run out of oil in 100 years from now, we have another million years or billion years before we get the next batch of stuff. So practically it's not renewable really. If you're out of coal, you got a long time to wait, and we don't have, our lifetimes are not that long to take advantage of this. So let's talk about actual times, right? For oil and natural gas, the depletion time predicted is 50 years. Bear in mind, my source came from the late 90s. So you have to subtract some years here. If it says 50 years, it's probably close to 30 now or less. Scientists predict that in our decade, which is between 2010 and 2020, the amount of usage will peak. So we must be at it about now. And following this, there will and have to be a redistribution of energy sources, because this just cannot go on. Coal, in spite of the debate that's ongoing in our nation about coal, its continued use or de-emphasis on coal, the one thing you have to know is it's an abundant resource. Its depletion time is a little over 200 years. This is lots of coal. The problem with coal is not its availability. The problem is the mining of coal and its combustion is environmentally damaging. And so that's something to keep in mind. However, given that there's a lot of coal and coal combustion is well understood, and the fact that there isn't any other source of energy like solar or wind that competes and contends with the volume of energy that coal puts out, it's very likely, despite best intentions, coal will continue for some more years. It's not going to simply go away. But we should equally be aware of its environmentally damaging consequences from mining and combustion standpoint. Other things, nuclear energy, uranium has about the depletion time of oil and natural gas, which is 50 years. Nuclear power plants are said to be clean energy, meaning that in comparison to coal, there is no product of combustion. And there's not the release of carbon dioxide and so forth, which is very true. However, nuclear technology can be, as you well know, like electricity, man's best friend or worst enemy. So nuclear power plants, if for any number of reasons they get out of control, whether it's man-made or it's an act of God or act of terror, 3 Mile Island, Chernobyl, Fukushima seem to be happening every decade or so, reminding us and asking us to keep this always in the back of our mind. And spent nuclear fuel, there is no easy way of saving this or storing this. We have to put it out of sight, out of mind, right? So we dig deep in the earth or in the ocean, build big structures that have lead and concrete around it, and it's always the question of whose backyard, right? Nobody wants this in their backyard. So understandably, there is not very wide public acceptance. You will see some nuclear plants being built because of our demand being such, but you may not expect a whole lot of relief coming from here. The other sources that are being currently looked at, biomass is like, it's like firewood or other, stuff that you burn and directly get energy, like your fireplace, or burning oil. Hydroelectric, geothermal, solar, wind. Well, in the best possible scenario, as technology exists now, for various reasons, hydroelectric is at the mercy of nature, right? You have drought, you don't have rains. Well, that's, you're out of luck. Solar energy and wind power are pretty promising, and we've made a lot of strides. Yet we are at a point today where sometimes breaking even in terms of cost of technology and implementation and the returns may be somewhat questionable, but I don't want to undermine these upcoming sources. We should continually invest in these and try to improve technology. But I think as we get into current debates about coal and so forth, what we have to bear in mind is if we shut all coal plants in Texas tomorrow, we don't have a competitor to fill in the gap, which means unless you and I are willing to have our homes and offices go dark for a a significant amount of time, we can't just arbitrarily shut down coal plants. We may choose not to build more and more coal plants, but we need to take the emotion out of this and understand what's what. Hopefully this gives you some perspective.